Welcome to our comprehensive guide on three-dimensional vectors and their operations. In this video, we'll explore the 3D coordinate system, vector operations, the dot product, and the cross product. We'll provide intuitive explanations and walk through detailed examples to help you master these concepts. Let's begin with the 3D coordinate system. In three-dimensional space, we use three perpendicular axes: the x-axis, which typically points to the right, the y-axis, which points upward or forward, and the z-axis, which points out of the page toward us. Together, these three axes form the foundation of our 3D coordinate system. Any point P in this space can be described using three coordinates x, y, and z, and a vector v from the origin to point P is written as the ordered triple of these three coordinates. Now, let's discuss basic vector operations in 3 dimensions. Let's consider two vectors: u equals angle bracket 1, 2, 3 angle bracket, and v equals angle bracket 4, negative 1, 2 angle bracket. Vector addition is performed component-wise. When we add u plus v, we add their corresponding components. So u plus v equals angle bracket 5, 1, 5 angle bracket. Scalar multiplication involves multiplying each component by a scalar. For example, if we multiply vector u by 2, we get 2u equals angle bracket 2 for 6 angle bracket. Next, let's explore the dot product of two vectors, which is a scalar quantity, not a vector. The dot product of vectors u and v is calculated by multiplying corresponding components and then adding these products. Mathematically, it's written as u dot v equals u sub x times v sub x plus u sub y times v sub y plus u sub z times v sub z. The dot product has several important properties. First, it produces a scalar value, not a vector. Second, it can be calculated using the formula u dot v equals the magnitude of u times the magnitude of v times the cosine of the angle between them. Third, if the dot product equals 0, then the vectors are orthogonal, meaning they're perpendicular to each other. Let's calculate the dot product for our example vectors. U dot v equals 1 times 4 plus 2 times negative 1 plus 3 times 2. That's 4 minus 2 plus 6, which equals 8. Now let's discuss the cross product, which, unlike the dot product, results in a vector rather than a scalar. The cross product of two vectors, u and v, produces a third vector that is perpendicular to both u and v. It's calculated using the formula u cross v equals angle bracket u sub y times v sub z minus u sub z times v sub y, u sub z times v sub x minus u sub x times v sub z, u sub x times v sub y minus u sub y times v sub x angle bracket. The cross product has several key properties. First, it creates a vector perpendicular to both input vectors. Second, the magnitude of the cross product equals the product of the magnitudes of the two vectors times the sine of the angle between them. This magnitude also equals the area of the parallelogram formed by the two vectors. Third, the cross product is anticommutative, meaning u cross v equals negative v cross u. Let's calculate the cross product for our example vectors. For the x component, 2 times 2 minus 3 times negative 1 equals 4 plus 3 equals 7. For the y component, 3 times 4 minus 1 times 2 equals 12 minus 2 equals 10. For the z component, 1 times negative 1 minus 2 times 4 equals negative 1 minus 8 equals negative 9. So, u cross v equals angle bracket 7, 10, negative 9 angle bracket. Finally, let's discuss some applications of these concepts. The dot product is extensively used to calculate work in physics, which is the force applied to an object multiplied by the displacement in the direction of the force. For example, if a force of 10 newtons is applied at a 30-degree angle to move an object 5 meters, the work done is calculated using the dot product. Force.displacement equals 10 times 5 times cosine of 30 degrees, which equals 43.3 joules. The cross product is used to calculate torque in physics and to find normal vectors in computer graphics, which are essential for determining how light reflects off surfaces. To summarize what we've learned, the 3D coordinate system gives us a framework to represent points and vectors in space. Vector operations like addition and scalar multiplication help us manipulate these vectors. The dot product gives us scalar information about vectors, like the angle between them, and the cross product produces a perpendicular vector and is crucial for many physics and engineering applications. I hope this comprehensive overview helps you understand these fundamental concepts in vector mathematics.